Let us now dive in to the main topic of our discussion, which is impedance. Now, my goal is to help you understand and appreciate impedance a little better than how you currently understand it. Okay, I would like you to walk away from this session having a very clear appreciation of, understanding of, comprehension of resistance, capacitance, inductance, and how the frequency comes into play and how they basically modify their behavior, if at all, with the changes in frequency. And as we package them under this definition of impedance, what will their behavior be like? Make sense? Because the fact of the matter is that impedance is actually an umbrella term that we use, which encompasses your resistance, your capacitance, and inductance. And more specifically, more precisely, it packages your resistance and your reactance. The title of the webinar is Impedance, Resistance, and Reactance because reactance is basically capturing the effect of capacitance and inductance. So when we think about impedance, I think at a base level, interpreting impedance as resistance is probably a decent start, but it is inaccurate. Why cannot we call impedance simply as resistance? Is there any issue with that? Because impedance is like you're impeding my way, you're blocking my way, right? Resistance is also like you're resisting my path, right? You're resisting my way. So intuitively, they are both sort of doing the same thing, at least from a standpoint of, the language. But when we look at the definition, when we look at the makeup and composition of impedance, we realize that impedance is actually the umbrella under which resistance resides. And there is also another element. The other element is the reactance. Okay, so we need to be very clear about that. The real part of impedance is basically your resistance. So this is the real part of impedance. The imaginary part of impedance is your reactance. Okay, so when we talk about Ohm's law actually applies to impedance, it applies to resistance, it applies to reactance. Okay, V over I. And you would have seen that a lot of times to sort of cover all the bases, Ohm's law is stated as V is equal to I times Z. Okay, the more simplistic, the more common definition is V is equal to IR, but the more accurate one is actually this, or the one that basically captures all the different scenarios is this definition, because the impedance that you have may only be purely resistive, or it could also have a reactive component to it. Now, resistor is a device that is independent, that whose behavior is independent of the frequency. Make sense? So you have the resistor over here. When we basically set this as the ratio of our voltage to the current, right, which is the impedance, it will turn out to be R if we only have R in the system. Okay, if we don't have any reactance in the system, when we have purely resistive components, and resistors sort of look like this. If you have experience with some circuit analysis labs and power systems labs, on the breadboards and whatnot, you see these small devices. So that's how the resistors look like. They are color coded. So the color schemes, basically the first letter reading from left to right would mean something, and the second letter would mean something else, and the third letter would mean something else. It's like decimal points, right? But frequency independence, this is a key parameter. This is a key feature of a resistor. You bring up the frequency to 0, you bring up the frequency to infinity. A frequency of 0 is DC, a frequency of infinity is basically a AC system, with very large number of oscillations, okay? Then we look at capacitance, which actually resides in the imaginary component, reactance, okay? So capacitance behavior, so if you have a purely capacitive impedance, that V over I is made up of the impedance, which is purely capacitive, it will take the form of 1 divided by j omega c. And the interesting part over here is that all of a sudden we have frequency at play, right? And the way the frequency impacts the impedance is that since frequency is in the denominator, right? If we set the frequency to 0, any number divided by a 0 goes to infinity. So Z becomes infinite. So a purely capacitive load to which DC is applied, okay, the voltage is not changing, the frequency is 0, will act as an open circuit. And it is a deeper concept. I have multiple lectures on this particular topic as to how the capacitor acts as an open circuit for DC, but during transient state, it starts charging and discharging, okay? And when you increase the frequency, you keep on increasing the frequency, the impedance actually goes down to 0. It becomes a short. All you need to remember over here, and whether you're preparing for the FE electrical or P power, you don't actually even need to memorize any of this, is to pay attention to where the omega is appearing. Okay. And if you're just starting out with your review of impedance, the crucial point is that the omega is appearing in the denominator. So from a mathematical standpoint, as we increase the frequency, this value actually decreases. Okay. And when the frequency is at its lowest, it will be at its lowest when we have a DC. So the frequency is 0. Impedance will basically be infinite. All right. Now in this V divided by I, if I have a purely inductive component or inductor, then the ratio of V to I is actually going to give me an impedance which will be j omega L. In the case of inductor, if it's easier for you to sort of visualize, imagine there is a 1 below it. And the reason I'm emphasizing this is that when we look at the impedance of a capacitor, you have this 1 appearing in the numerator. So it's easy to make the connection that your omega is in the denominator. Okay, so increasing the omega will reduce the impedance of the capacitor. Decreasing the omega will increase the impedance of the capacitor. Okay, by putting this 1 underneath j omega L, what we basically realize is that now we have a direct relationship with omega. So when I am reducing the value of frequency, okay, then the impedance is directly proportional. So it basically reduces. And when I'm increasing the value, it basically increases. So this is at a fundamental level, understanding, how impedance is, what impedance is made up of, what are the three elements. You have resistors, you have capacitors, and you have inductors. Now, the fact of the matter is that this holds true for something we call as actually linear elements. Okay. Your R, L, and C, your resistor, inductor, and capacitors are called linear elements. You guys know why they are called linear elements? What type of linearity are they holding? They are linear because V is equal to IZ applies on them. The linearity over here is that the voltage is directly proportional to the current. Okay, and this is Ohm's law. So your resistors, it's also a good interview question. You get asked on an interview that give me examples of some linear elements, right? You'd be like, yeah, I know 3 linear elements, resistors, inductors, and capacitors. Follow-up question, why are they linear elements? Because they hold the linearity for Ohm's law. Okay, can you explain? Sure, V is equal to IZ. You see this proportionality sign? When you turn it into equality sign, the thing that remains constant is Z. And this Z can take the form of resistor, can take the form of capacitor, can take the form of inductor. Another follow-up question. Can you tell me some examples? Give me some examples of non-linear elements. Well, they are the ones that don't hold Ohm's law, that for which the Ohm's law does not apply. Okay. Give me some circuit elements. Give me some specific cases. Sure. Your PN junction diode, right? Because the PN junction diode does something like this, correct? In terms of the voltage current relationship. What else? Your transistors. The relationship between voltage and current is not linear in all the three modes of operation. You're talking about BJTs, then you have cutoffs, you have linear region, you have amplification. Same thing for MOSFET, right? So this is level 3 understanding, which I tell my students to aim for, right? If you are just going by the formulas and the equations and the mathematical details that are provided in the reference handbook, if somebody wants to test you on one level above that, try not to find yourself in a situation where you're not able to sort of tackle those type of questions, especially for the PE Power exam. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE Power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE Power exam preparation programs, please visit my website, StudyforFE.com.